Here's a challenge. I got 5 x positions 0, 3, 6, 9, 12 and 5 y positions, same values. I want a grid of 25 points, every x paired with every y. Almost every Grasshopper beginner tries this and gets 5 diagonal points instead of 25 points. Today, you'll know exactly why that happens and exactly how to fix it permanently with one single right click.
Open a fresh canvas. Double-click canvas, type series, place it. Rename series X. Set start 0, step 3, count 5. Double-click canvas, type series, place a second one. Rename series Y. Set start 0, step 3, count 5. Double-click canvas, type construct point, place it. Connect series X output to construct point input X. Connect series Y output to construct point input Y. Leave Z input at its default of 0. Look at Rhino viewport, 5 points, in a straight diagonal line, not a grid. Here's exactly why. Grasshopper matched these two flat lists, item by item, position for position, the same way we saw two flat trees matched on day 9. X's item 0 paired with Y's item 0 giving 0.00. X item 1 paired with Y's item 1 giving 0.33. 5 pairs in, 5 points out, a diagonal, because each X value only ever met with the Y value, sitting at its exact same position. We got 5 pairs, but we wanted 25 combinations, every X meeting every Y. That means we need to break the one-to-one pairing on purpose. That's exactly what Graft does. Right-click directly on an X input of construct point. In the context menu, choose Graft. Observe, a small arrow icon now appears on the X input, showing Graft is applied before the data arrives. Switch to the Rhino viewport. 25 points, a perfect 5x5 grid. Here's why that single right click fixed everything. Crafting the X list turned our 5 flat X values into 5 separate branches: 0, 0, 1, 3, 2, 6, 3, 9, 4, 12. The Y list is still flat, one branch holding all 5 values together. Now, Grasshopper has to match these two structures. Each of the 5 X branches, each holding just one value, get matched against the Y input's entire branch of 5 values. One X branch into 5 Y values equal to 5 points. Repeated across 5 X branches gives 25 points in total. That's exactly the tree matching behavior from yesterday's lesson now puts to real use. As an alternative demonstration, undo the right-click Graft and instead insert a standalone Graft tree component between series X and construct points X input. Same result, same underlying mechanism, just a visible component on the canvas instead of a small icon on the wire. Either approach is correct, use whichever is clearer for the file you are building. Remove the standalone Graft tree component and reapply the right-click Graft directly on the X input to keep the canvas clean for the rest of the lesson.
A common beginner question: why craft X specifically and not Y? The honest answer is, it doesn't have to be X. Crafting Y instead and leaving X flat produces the exact same 25-point grid, just built by column instead of row by row. What matters is that exactly one of the two inputs is crafted and the other stays flat. Craft both and you'll get a nested 9 branch structures that still contains 25 points, but organize them in the way that makes later operations more confusing than necessary. Craft neither and you'll back to the 5 points diagonal.
Double-click canvas, add a number slider set to integer range 2 to 20. Current value 5. Rename column count. Double-click canvas, add another number slider range 1 to 10. Current value 3. Rename column spacing. Connect column count to series X count input C. Connect column spacing to series X step input N. Add row count integer 2 to 20 default 5 and row spacing 1 to 10 default 3 sliders. Connect them to series wise count and step inputs respectively. 4 sliders now fully control the grid. Drag column count to 10, 10 columns appear. Drag row count to 10, now 100 points grid. Adjust either spacing slider and the whole grid scales evenly. Complete parametric control from 4 numbers. Double-click canvas, type XY plane, place it. Connect construct point output to XY plane input. Double-click canvas, type center box, place it. Connect XY plane output to center box input. Now, add 3 number sliders. First, panel width 1 to 3 default 2. Second, panel depth 1 to 3 default 2. And lastly, panel thickness 0.1 to 0.5 default 0.2. Now, connect panel width to X, connect panel depth to Y, and connect panel thickness to Z. Center box builds a box centered exactly on a plate. Its X, Y, and Z inputs are the full size of the box along each direction centered on that plane, not a distance from the center to one edge the whole span. That's why the panel width of 2 gives you a box that extends 1 unit in each direction from the grid point for the total width of 2. That's a complete parametric facade panel system. 100 panels, every one identical, and every part of it, grid density, spacing, and panel size, is controlled entirely by sliders. This exact structures, refined and extended, is the foundation behind essentially every parametric building facade you ever seen.
Your day 10 challenge, the attractor pattern, one of the most recognizable techniques in parametric design.
Double-click canvas, type point, place a point parameter. Right-click it, set one point. Click anywhere near the grid in the Rhino viewport to place your attractor point. Now, double-click canvas, type distance, place it. Connect the grid's construct point output to distance input A. Now, connect the attractor point parameter to distance input B. Add a panel to the distance output D, rename it distances. This gives you one distance value per grid point, how far each point sits from your attractor. Points close to it get small numbers. Points far away gets large ones. Double-click canvas, type remap numbers, place it. Connect the distance output D to remap numbers input B. Set a target input T domain to 0.3 to 1. Connect the remap numbers output R to replace the fixed panel width and panel depth slider connection on center box, feeding this remapped value into X and Y instead. Remap numbers takes each distance value and rescales it into a new range you choose. Here 0.3 to 1. So instead of feeding center box a single fixed panel size, every panel now gets its own size based on how far it sits from the attractor. Points far away from the attractor gets panel near 1 in size. Points close to it string toward 0.3. Move the attractor point parameter around in the Rhino viewport. Watch the whole panel pattern response as you move that single point. That's the attractor field. A handful of components and the entire facade reorganizes itself around wherever you place one point.
Summary of this video. Two flat lists connected into the same component get matched position by position, which is why exactly two flat coordinates lists produce a diagonal line, not a grid. Crafting exactly one of the two inputs breaks that one-to-one pairing and produces a full cross-reference grid instead. That same grid, once built, can be driven by sliders for full parametric control and can vary any geometry. Here, center box panels across every point. Distance and remap numbers turn that static grid into an attractor-driven pattern. Components used today: series, construct point, XY plane, center box, point parameter, distance, remap numbers, and construct domain. Day 11 moves into math and expressions, the tools that will let you drive every slider you have built so far with formulas instead of by hand. Subscribe and I'll see you there.